string will vibrate in 3 segments. Now look at these segments. This is the third mode of vibration. You have a node there, a node, a node, a node. There are 4 nodes. And how many antinodes? An antinode, an antinode, an antinode. The frequency of this is 3 times the fundamental, and you call it the third harmonic. So the fundamental, twice the fundamental is the second harmonic, 3 times the fundamental is the third harmonic. Now for the third harmonic, the length of the string contains, now if you notice, this is the total length of the string. The total length of the string contains now how many waves? Now, one full wave is a distance between 2 alternate nodes. That is one full wave, and this is a half wave. So, the length of the string now contains a full wave and a half wave. In other words, it contains 3/2 wavelengths. That means lambda equal to 2/3 of the length. If this is the length of the string, wavelength is this, which is 2/3 of the length of the string. Alright, so what is the equation for the frequency of the third harmonic? F3 equal to V over lambda, and lambda equal to 2/3 of L. So replace lambda by 2/3 of L. Now this can be written as 3 will go up, is that right? That will be 3 times V over 2L. I hope you understand that. And what is V over 2L? V over 2L is the frequency of the fundamental. So that will be 3 times F1. The frequency of the third harmonic is 3 times the fundamental. Now I have the diagrams illustrating many more modes of vibration. Look at this. The fundamental mode of vibration, the frequency is 1V over 2L. The second harmonic, the frequency is 2 times V over 2L, 2 times the fundamental. The third harmonic, the string vibrates in 3 segments. The frequency is 3 times the fundamental. The fourth harmonic, the string vibrates in 4 segments. The frequency is 4 times the fundamental. Fifth harmonic, the frequency is 5 times the fundamental, and so on. Alright. Let's now talk about quality or timbre of a musical note. Now, do you know that a guitar is actually a stretched string? When you pluck it, the guitar wire will vibrate, and it can vibrate giving out its fundamental frequency, the second harmonic, the third harmonic, and so on. But most of the time, when you pluck a guitar wire, it will be vibrating in its fundamental mode, that will be in 1 loop. But along with the fundamental, the string can also vibrate in higher harmonics. And it is this phenomenon that contributes to the quality of a musical note. Now, what is the meaning of quality of a musical note? When the stretched wire of a piano or guitar, piano is also using stretched wire to produce the musical note. It vibrates with notes at fixed end and antinodes at the center, emitting its fundamental frequency. The sound you hear when you strike a piano key is actually the fundamental frequency of one of the wires. If you open up a piano, you actually will see a large number of strings. Each string has a particular length, and you know the length will determine the frequency. the fundamental frequency. Remember, the fundamental frequency is V over 2L. So if you change the length of the string, the fundamental frequency of vibration will change. So this is the basic or fundamental mode of vibration of a guitar wire or a piano wire. Now, along with the string vibrating in this fundamental mode, a string can also vibrate in higher harmonics. In other words, the higher harmonics are very often superimposed on the fundamental. So the sound you hear is not only the frequency of the fundamental, but a combination of the fundamental and the higher harmonics. Now, it is this combination of the higher harmonics with the fundamental that gives a musical note its quality. And the quality of the musical note can be used to distinguish between a note that comes from a piano, or a note that comes from a guitar, or a note that comes from a drum, or a note that comes from a piccolo, or a note that comes from a flute. You see that? They are all musical instruments. A particular note means a particular frequency. Although all these musical instruments can produce the same frequency, they will all sound different. It is that difference we call timbre or quality. And what is the contributing factor for the timbre of a musical note? It is, along with the fundamental, the vibration can also be in the higher harmonics. It is the combination of the higher harmonics. In different musical instruments, the combinations of the higher harmonics will be different. And that difference in the combinations of the higher harmonics produces that particular timbre of the sound that comes from a particular musical instrument. Alright? Let's now obtain a wave function for a stationary wave. A stationary wave function. Now, do you remember how stationary waves are formed? Stationary waves are formed when an advancing wave and the reflected wave superimpose on each other, and the resultant wave is the stationary wave. Standing waves are formed by the superposition of two homogeneous waves. What does that mean, homogeneous? They are identical in amplitude, frequency, and wavelength, because it is the same wave, advancing wave and the reflected wave. The same wave gets reflected. They are basically the same wave. They are homogeneous. But one is advancing to the right and the other is advancing to the left. Let me ask you. In the last lesson, we developed equations for a harmonic wave advancing to the right and a harmonic wave advancing to the left. Do you remember those equations? Well, y equal to a sine kx minus omega t is the equation of the wave that advances to the right. Y equal to a sine kx plus omega t is the equation of the wave that advances to the left. So a wave function for a wave advancing to the right is y1 equal to a sine kx minus omega t. And a wave function for a wave that advances to the left will be y2 equal to a sine kx plus omega t. And these two waves now superimpose each other. That means the resultant displacement at any segment of the string will be y1 plus y2. Alright, what is y1 plus y2 equal to? Now remember, in this case, k. K is called the, what's the name for K? I told you not to confuse it with the spring constant. It is not a spring constant. It is just the wave number given by k equal to 2 pi by lambda, and omega is called the angular frequency, which is 2 pi f. Now the sum of these two waves is y equal to y1 plus y2, a sine kx minus omega t plus a sine kx plus omega t. Now, can you use the equation I gave you in the last class? Sine of A plus sine of B, and expand this? Well, we can expand this using the trigonometric identity we used in the last class. Sine of A plus sine of B is 2 cos A minus B divided by 2, or 1/2 A minus B, times sine of 1/2 A plus B. Our A is kx minus omega t, B is kx plus omega t. So that will be, when you add them, you get 2a, this a will be common that comes out, that will be 2a cos omega t sine kx. Is that right? If you subtract kx minus omega t minus kx minus omega t, will be negative omega t. Is that right? 1/2 of negative 2 omega t will be negative omega t. And cos of negative omega t is cos omega t. So the resultant wave is y equal to 2a cos omega t sine kx. And this is the equation for a stationary wave. So the equation for a stationary wave is yxt equal to 2a cos omega t sine kx. Okay. Let's now talk about the laws of transverse vibrations of a string. What are some of the fundamental laws that governs the transverse vibrations of a string? What is the meaning of transverse?